Hello. Hey, everyone. Thanks for joining. My talk is about building xChain, cross-chain applications with Connext. Oh, sorry. Okay, so just as an intro, my name is Rahul. I'm the co-founder and CTO of Connext. I've been in the space since about 2017. We started Connext in 2017, so we've been around for a long time. Been doing a lot of different things in this space, like state channels, fiat on-ramps, DAOs, and now we've actually moved into interoperability, which we think is a really cool space. So just to give some background, this is how the old world, like back in the day in 2016, 2017, et cetera, used to look. You had ETH, you had Bitcoin, you have these very kind of distinct and separate ecosystems where there was no real way to link between them. Like if you have funds on Ethereum and you want to get to Bitcoin, really the only thing you could do pretty much is go through a centralized exchange. And now what we're seeing come together is a multi-chain world. So you have these distinct clusters of different chains that are popping up all over, and they have these very distinct ecosystems between them. So you have ETH plus the rollups, they're sort of forming this own little cluster. And then you have Cosmos, which has its own little cluster as well. And you also have Polkadot, and now you have even things like Polygon is launching like these things called supernets. Avalanche has subnets. BNB has these app-specific chains. So you're really kind of starting to see multi-chain as in a multi-cluster ecosystem. And with that, we get to what bridging means in this new multi-chain world. So the first type of bridging is intra-cluster bridging. So that means you have like these little connections within these little clusters. And some of these ecosystems have done this really well. Like for example, Cosmos has built IBC. So from the get-go, they wanted this thing called intra-cluster communication. So they built inter-blockchain communication as the IBC protocol. Also, Polkadot has XCM. So these, in between these little clusters, you have this communication that's a very powerful communication tool. Polygon, Avalanche, all these other cluster-based ecosystems are all building bridges in between like this. But then you get to this harder problem where you have like this problem of how do you get from rollup on Ethereum to this chain on Cosmos, then to Polkadot, then back to some other rollup. So that's where you have like kind of like a harder problem that is not solved by these intra-cluster bridges. Now, like what exactly is a bridge? So let's back up and figure that out. So a bridge is you have Alice who's on origin chain A wants to send a message to a destination chain. So she will say something on an origin chain, then something happens, some kind of magic process, then you get something to happen on a destination chain. And then this can either be, this can be like sending tokens, this can be sending messages, this could be like sending data, this could be a smart contract call. It doesn't matter what it is, but something has to happen. So let's dive in and figure out what is this magic. So there's a few different ways that you can bridge, and I'll try to talk about some of the main ways that we've thought about bridging so far. So natively verified bridges, that means a chain's own validators verify the TXs. So this, if we go back to this, sorry here, I'm gonna back up a little bit, but this intra-cluster bridging is built using natively verified bridges. So in practice, a natively verified bridge means that a chain's nodes are running light clients of all the other chains within this cluster. Like if you go to rollup bridges, all the Ethereum nodes are actually verifying the transactions that are going on in rollups. If you go to Cosmos IBC, every Cosmos node that has an IBC connection to another Cosmos node is running a light client validator of that other chain. So this is probably the most secure and best way to bridge. But the problem is it's not generalizable. Like you can't have Ethereum validators validating transactions on Cosmos. That's just never gonna happen. So the problem with this, the trade-off that you get with this type of bridge is that it's not generalizable. If you wanna solve that trade-off, you can do this other kind of type of bridge, which is called an externally verified bridge. This means you have a third party of validators. So you have this set of validators that uses proof of stake, multi-sigs, other things like that to validate a transaction from one chain to another chain. And this solves the generalizability problem, but now you get into an issue where this is not trust minimized. You have to actually trust the validators of this bridge. And then you have another way you can do it, which is a locally verified system. So this means you have an off-chain counterparty that verifies from one to the other. So if you want to bridge from, let's say, chain A to chain B, you will run some kind of off-chain client that verifies that the transaction was done on chain A and can be done on chain B. So an example of this is like an atomic lock or a hash lock based bridge. So these have been pretty popular in the past. They're really good for like just transferring funds, but the trade-off here is that they're not extensible. So basically the bottom line is each of these kinds of bridges comes with their own different sets of trade-offs. That brings us to this thing called the interoperability trilemma. As you know, we're all in the blockchain space, so we love trilemmas. So this is the trilemma that comes with interoperability. You have, on one side, you have extensibility, which means I want to be able to compose my bridge with other smart contracts, essentially make it like a DeFi building block. You have generalizability, which means I want to be able to paste this bridge and connect to every single chain in the world. And then you have trust minimization, which obviously you want to be able to not have to trust some set of parties that doesn't have your best interests at heart. So you can see the different kinds of bridges that we've outlined before. You have the MPC Oracle Validator Bridge. On one side, you have the Atomic Lock-based bridge, which is the locally verified system on the other side. And then you have Light Client Relays, which is the natively verified system. So all of these different bridges, unfortunately, have trade-offs. So how do we solve this trilemma? Well, there's a new kind of bridge design that has kind of become popular fairly recently, and Connext has kind of like written a lot about this, so I'd really encourage you guys to look into some of the writing that we've done about this. So this is an optimistically verified bridge. So this system is slightly different because you have a message that's going from chain A to chain B, and then this is not like an instant system. So before the message on chain B is determined valid, you have a set of actors in the middle, one of n, that can prove fraud. So they're not in charge of like holding funds or like, they don't have any control over funds. What they can do is they can basically pause the bridge if anything goes wrong. And then this brings its own trade-off where it's not instant. So now we go from a trilemma to a quadrilemma, which, that's annoying because, you're just adding a new trade-off here. But there is a solution for this as well. So this is kind of like the holy grail type solution. So you have an optimistically verified bridge, but in the middle you have this little pink thing, which is a liquidity provider. So the liquidity provider can come in during the fraud period and basically like front run the fraud period to actually send the funds to the user on behalf of this optimistically verified bridge. And so essentially the liquidity provider takes the lockup period, but the user does not have to experience any type of lockup. So with fast liquidity and optimistic bridging, we can basically solve this quadrilemma. Okay, so this brings us to like hacks. Bridge hacks are kind of like the flavor of the month or the flavor of the past few months. Everyone is aware that bridges have been getting hacked left and right. I think what this shows mainly about our space is that bridges are a huge weak link in the system. They're pretty new technology, so they're like a huge honeypot of attacks. What I think is that like this is just new technology that is being experimented with still, and it is a huge basically target, and it's kind of going through a trial by fire process where blockchains themselves have been through this trial by fire process. They're battle tested technology now. Bridges are kind of going through this trial by fire. But with that said, I think this optimistic version gives us a very good way to sort of like mitigate the effects of hacks and security because of this fraud-proof window. So like I said, you're going to have some time between message A and message B to actually do some kind of checks. So these watchers in this fraud-proof based system are looking for fraud, but they can also look for other things. Like if you say some stablecoin got depegged and you want to immediately like stop the bridge, you can do that with this kind of like fraud period. So the watchers can check for more than just fraud. They can check for suspicious activity and bring us to this thing called a circuit breaker. So basically you can just like stop the bridge and stop the process, and you can basically mitigate the risk of users losing funds, liquidity providers losing funds, and kind of this whole like crazy consequences of these bridges being hacked. Now we're going to get into developing Zaps, which is cross-chain apps. Going on this whole X motif, Connext, we have developed this new interface and this new paradigm called xCall. So this is a low-level primitive to facilitate asset and/or data transfer across arbitrary chains. It's designed to mimic Solidity's built-in call method. The way we're approaching the developer experience for cross-chain applications is that we want it to be as easy as possible for developers to pick up and learn the process of cross-chain. What we've seen when we've gone to hackathons and we've interviewed developers is like a lot of them are interested in the idea of cross-chain, but they find it really hard to wrap their head around what it means to actually develop a cross-chain system. So we're trying to make that as easy as possible by creating this new primitive that matches basically the built-in version of Solidity, so developers don't really have to learn anything new. They can just kind of like augment what they already know in terms of like how to develop decentralized applications. Okay, if we want to look at a little bit of code, I apologize if this is small, but this is basically the xCall primitive in action. So as you can see, what we're trying to show here is that this is a very simple function signature. It has a bunch of params in it, and there's a single call. So all you do is you initialize your Connext handler contract, and you call xCall. And the args in here are quite straightforward. So I'll just go through some of them. The to address is who is going to receive the funds on the destination side. Call data, this is something that's very important. So what you can do here is you can pass data through. So if you say, I want to call a contract on the destination side, what you would do is you would encode the data. So you can see we're just calling encode with selector, then we're hashing the name of the function. So this is the function signature hash. So this is exactly what gets called in Solidity on the destination side. So we're calling a function called update value. It takes a uint 256 and is calling it with some number we want to update it to. Then you have origin destination domain. So this is just encoding of what the chain you want to go to and from. Agent recovery, so this is kind of just some like fallback parameters. So in case the transaction fails on the receiver side, then you have a way to like get the funds back. Force slow, receive local, these are kind of like not very important parameters that are kind of like advanced configuration parameters. Callback fee, we'll get into this a little bit later. This is also important. And transacting asset ID and amount. So basically what we've done is we made it really easy to send funds across chain and also send data if you want. So transacting asset ID and amount are basically the token that you want to send. So if you're saying you want to send like DD token on Gorley chain to Mumbai chain, which is what the origin destination domain are, this is basically the signature you have here. So what this is going to do is it's going to send this amount of this asset to the destination domain and as well as call this function. So when we get into call data, when I talk about data passing, you have distinctive flavors of data. So it's important to know that there's like two different types of data. When you're passing data, there's a type of data that's called authenticated data. This means the destination target needs to verify the origin, source, domain, and address. So you need to be able to verify on the destination chain that this came from a specific address on the origin chain. For example, if you're voting in a DAO on chain B from chain A, you need to know that the person on chain A actually voted in that DAO. So that's very important to verify that this came from the bridge. So in this case, that needs to come through this fraud-proof window. So you can't bypass the fraud-proof window in this case. However, there's another type of data called unauthenticated data. This means this is like a meta transaction. So the destination target does not need to verify the origin, source, domain, or address. So for example, like, and these use cases are actually more than you might think. So a swap can be done by anyone. It doesn't check message.sender. If I want to deposit into Aave, I can say I want to deposit on behalf of somebody else. So that doesn't check message.sender. If I even want to like check that an EOA on chain A signed a message, I don't need a message.sender. I can just check a signature. So this is an example. These are all examples of things that can actually be done very quickly through a liquidity provider. So the whole key to this is that you don't know who is going to fulfill this transaction on the receiver side. It's not going to be done through a bridge contract. It's going to be done through an external actor who is a liquidity provider. So because the data is not authenticated, this could be done fast. And you can see this little like pink guy there can instantly do this. So if you want to essentially do like a cross-chain swap where you swap USDC for like Ethereum, you can do that by doing this fast path. So it'll send the USDC through the bridge, and then it'll swap it immediately through the liquidity provider calling a Uniswap contract or something on the destination side. Then you get into a thing about gas. So how are you going to pay for gas? Like, essentially we want the system to be sustainable, so we don't want to be doing gas subsidies. A lot of other bridges do things like gas subsidies and things like that, but this is not sustainable. We want all the gas fees, everything that everyone who is a relayer in the system or liquidity provider, all their gas should basically be reimbursed by the user. So that's one of the desired properties, is that the user pays for all the gas fees. Another desired property is that the user does not need gas on the destination chain. This is super important because we want this UX to be extremely abstracted. Basically, our end goal at Connext is that you don't even need to think about what chain you're using. Like XApps, dApps should be building cross-chain systems that basically abstract the entire process of chains. So you should say like, I want to deposit from any chain, do something on any other chain, get the funds back on any other chain. And like all that process should be handled by the bridge itself. So the main point is that users don't need to have gas on any of these destination chains. But at the same time, we want to make sure that relayers are properly incentivized to submit these TXs. So we don't, like I said, we don't want any kind of subsidies or things that are not going to be really sustainable long term. So this is kind of a complicated diagram here, but we can walk through pretty easily. So on the origin side, Alice is going to pay for the gas fee on the origin chain in the native asset. So for example, if the origin chain is Polygon, Alice is going to add some extra Polygon, like in addition to what the transaction fee is for this transaction, which is going to basically be locked on the side, on the origin side, as a claimable relayer fee. Then we go through the bridge. The relayer, who is the one who does the fast liquidity stuff on the destination side, will basically complete this transaction, send it to the user on the end user on the destination side. Then once they do that, they will actually submit this proof back through the bridge. So it goes back, and then they are able to claim the relayer funds. So they prove that they sent the transaction on the destination side, and then they're ready to claim the funds on the sender side. This brings us to asynchronity. So when you're doing cross-chain app development, you can't assume synchronity anymore. So what does that mean? So blockchains are synchronous. That means everything happens in one transaction. It's an atomic transaction. So either the entire transaction goes through or it doesn't. So you don't have to like worry about anything. And this gives us basically all the properties of blockchains that we like. Like you can do Uniswap swaps. The reason Uniswap works is because it's synchronous. The reason flash loans work is because it's synchronous. So when you're doing cross-chain stuff, you actually lose that synchronity, and you have to kind of think about how you're programming stuff very differently. But the interesting part is that like we already do asynchronous programming everywhere. So if you're a developer, you're developing in JavaScript, you're developing anything on the internet with distributed systems, you don't have synchronous environments. You have basically, you send a call somewhere, you do some work with the callback, essentially. So you just send your call out, and then it processes something later. So this is a very common pattern in functions like Java, or in languages like JavaScript. For example, you have this .then call. So you do some work, which is an asynchronous process. You have a callback that you attach to this function. So now this .then function gets called sometime in the future. You don't know when, but you have some handler function written that can handle it when that happens. Okay, so now if you want to do this same thing in a cross-chain world, it looks a little different. So you have your origin chain, you do some work on the origin chain, then on the destination chain, you will do some work back on the origin chain once that process actually happens on the destination chain. So basically you're going to like tell something to happen on the destination chain, and then you're going to get the result of that back on the origin chain. And that's basically how a cross-chain callback works. So how does this work in Connext? Like I mentioned before, there was this callback parameter. Let me see if I can go back to this slide. Sorry, I'm going to go back here. I just want to make sure. So we have these parameters called callback and callback fee. So this callback, if you set this, you can set this to address this if you want this address to actually implement the callback. Sorry, I should have included that in the parameters. But there's a very simple way to basically set it so that you're going to get the result of the call that you make on the origin side from the destination side. So for example, we're calling this function called update value. If update value returned a result, basically like a true or false or something, whether or not it was updated, then you would get the result of that on the callback address if you specify something other than address 0. So in theory, you would specify address this. So let's go back here. So then we have our xcall function, which does some stuff, and then we have callback. So all we have to do is specify a function called callback, and then we specify only promise router, which means we're going to verify that this data is only going to come from the bridge. And then we have some handler which you know, in this contrived example, all it does is update the data on one smart contract with the result of the callback value. So this is a very simple interface for implementing asynchronous solidity, essentially. And what are people building? So, you know, I think this kind of unlocks a really cool set of use cases for cross-chain apps, and we're starting to see now that there are more and more things that are being built with cross-chain applications. For example, Superfluid is a company that's building on Connext. They're building cross-chain money streams. We have Keeper, which is building cross-chain Uniswap TWAPs. This is really important. This is going to be like a DeFi building block. So essentially, you have a Uniswap TWAP, which has liquidity on one chain, but you want this price to be carried to other chains as well. But you can't guarantee you have liquidity on these other chains. You can only guarantee you have liquidity on the chain where you have liquidity. So instead of fragmenting the liquidity and making the whole TWAP more unsafe, you can just move the TWAP price from chain to chain. FujiDAO is another project we're working with. They're doing cross-chain lending aggregators. So like I said, we want to be able to make the cross-chain process kind of completely abstracted from the user. So that means users should be able to get yield from any chain they want without even thinking about what chain they're getting. So FujiDAO is helping make this happen. NFT Hashi is another project we'll be collaborating with. They do multi-chain NFTs. So NFTs are something that should be able to be on any chain without really worrying about which chain they're minted on. So they're making this happen. And DAO governance is a really important thing. So you want to be able to vote from one chain to a DAO on another chain. This is just something that should be there and should exist. So why not? And then this brings us to what we want to see next. So we want to see builders taking this to the next level and really figuring out what the next applications of cross-chain are. So the world is basically the oyster at this point. There's a lot of things we haven't even thought about here. So cool, thanks for listening, everyone. These are the links here. If you want to get more involved with Connext, please reach out to me. If you have cross-chain app ideas, we'd love to talk about it. And yeah. If anybody has any questions, happy to stick around and answer, or can find me later.